Hi everyone. Today's session, relative humidity. That's in the built environment, of course. What we're going to do is just going to take a look at a few generalized points of relative humidity. I'm sure everyone's heard of the term, and I'm sure most people kind of are in a position to kind of explain it. But we need to know much more about relative humidity because it is an absolutely critical factor in the design process. And if we get this wrong, this isn't just about real compromise in human health. This is a real compromise in human safety. This can bring structures down. This does bring structures down. Believe it or not, humidity can be absolutely catastrophic. And we're going to take a look at the actual design process and how that's involved. But let's have a look at a few initial things about relative humidity in the first instance, and let's acquaint ourselves with what it is. The images on the left, or the image on the left, that's the typical horse. We can see that it's a cold day, and you know that when we're outside, and we can see our breath on the air. What actually is happening? Have you ever considered why the foggy, misty breath stays on the air for a few seconds and then disappears? Well, obviously we can just explain that and say, well, it's our temperature in our body, core temperature, around 36.2 degrees, is obviously warmer than outside. So therefore it's indicating that actually we're breathing water molecules or vapor. We're actually breathing that out. So what's happening is, well, let's take a look at it this way. Relative humidity is in fact it's when the temperature in the air has the potential to hold 100% maximum saturation, right? So for every 1 degrees centigrade, there is max potential for 100% saturation. So what that actually means is, if we take dry air, which is just a normal dry air temperature, I mean, if what we say is dry air would be 0 degrees. Okay, so there's no moisture in there whatsoever. It's only when we start adding moisture to the environment that we're in, that we actually feel more comfortable with what we're breathing in. So if we say that the usual settings, 21 degrees, and I mean, you remember the last session we did about human comfort and in conduction, convection, radiation, the range for a classroom, living room, etc. for humidity was around about 60%, and that the temperature on average was around about 18 to 25%. So if we take a classroom, 21 degrees, we're looking at no more than 60-65% of humidity, of which then usually mechanical intervention in the form of a HVAC, a heating, ventilation, air conditioning unit, replaces the air, takes the humidity out and replaces that. And sometimes people feel dry throat experience with air conditioning. Personally, I'm not the biggest fan of air conditioning, but on some hot days, and certainly in hot countries, it is a very welcome feeling. So getting back to this 1 degree. So for every 1 degree, there is a maximum potential for 100% saturation. So energy is heat, okay? Just one form, all right? So when we put energy into the air, that energy has the potential to hold the saturation. So as we can see the picture with the horse and the mist or the fog on the breath, what's happening there is that the moisture's coming out, and there's energy within that moisture. There's energy. And the reason why it dissipates very quickly is because the cold air does not have the potential. It doesn't have enough energy to actually hold that moisture. In other words, it's exceeded its maximum potential. If you picture relative humidity as a sponge, okay, and that sponge is a 1 gallon sponge, so it has the potential to hold 1 gallon, or in this case it has a maximum potential for 100% saturation. So if we put that 1 gallon of water into the sponge, then the sponge is at its maximum potential. If we add 1 drop of water to that sponge, that drop will come straight out because there isn't any potential to hold it. There's not enough energy in there. If we only put half a gallon into the sponge, then that would be 50% relative humidity. In other words, half the content is equal to half the potential for 100% saturation. So if we doubled the sponge, so we had a 2 gallon sponge and we had half a gallon of moisture, what would that equal? Of course, that would be 25% relative humidity as a percentage. And it's relative in size and capacity. So going back to a classroom, if we said that it's 21 degrees and 50% relative humidity, and then we suddenly turned the temperature up rapidly, very quickly, what do you think would happen? Okay, so we're applying energy into the air. Going back, for every 1 degree there is a maximum potential for 100% saturation. So just like the sponge, we're providing more temperature, more energy into the environment. Therefore it has a potential to hold a maximum 100% saturation. So if we went, say, from 21 degrees to 25 degrees and it was 50% humidity, the humidity relative would be dropping to probably 22%, because we've drastically upped the capacity for the dry air to hold more vapor, more water molecules. Now, if we take a look at the image on the right, it's an advertiser's dream, isn't it? It's like we always see the adverts there with these cold drinks with the ice cubes in. And have you ever wondered what all of this is on the outside of the glass? Well, I think we can all say, well, that's a condensation. But have you ever thought what it really is? Now, I hope you're not eating your meal or your dinner or your breakfast or anything of that nature at the moment while I explain this, but the average human being exhales approximately, wait for it, approximately 2 litres per 24 hours. 2 litres. Now, if we break that down hour by hour, let's say you go into a restaurant, okay, and you go in there and you're going to order a meal, you're going to order a drink. Let's say you bought a bowl of chips and a glass of Coca-Cola. I'm sure all the brands are available, but there you go. And you're in there for about an hour and a half. Okay, let's say 2 hours. You're really going to take your time, 2 hours. So what this breaks down to is for every 2 hours, you are exhaling approximately 166 millilitres of human vapor. Now, the reason I say human vapor, oops, I don't know where that's just gone. With the human vapor, that is all the things that comes from us. You know, you could have people with bacterial infections. You could have people haven't brushed their teeth for a few days, few weeks, even. Yeah, those people right there. They might be carrying a cold, all sorts of things, of which are all the molecules from all those bacterial infections and the general human funk, as I like to call it, is all being exhaled. So as all those people congregate in the restaurant, the temperature through obviously conduction, convection and radiation is now rising. There is now more possibility for more vapor to join the environment because the temperature is rising, so therefore there's a potential for 100% saturation. So let's say there's 80 people in the restaurant and they're all exhaling, they're all there for 2 hours. You can calculate how many millilitres that actually exhales. Now, a can of Coca-Cola, is 330 ml. You're there for 2 hours and you've just exhaled half a can. So let's say there's 100 people there. That's 50 cans, okay? 15 litres of moisture has been evaporated, exhaled into the air that you're breathing, all right? Now, because the glass is obviously a lot cooler than the vapour in the air, the dry air temperature, what happens is dew point happens. And we'll be going into this. I don't know what's just happened to that. Dew point. And we'll be looking at this in a lot more detail. That equals condensation. So whilst the drink on the right looks like it's a really appetizing and enticing, really refreshing, and it's going to cut through your thirst, the glass is also covered in potentially 99 other people's exhalation from their body, carrying all sorts of, well, whatever they're carrying. So the next time you order a drink and a bowl of fries, make sure that when you start eating your fries, you don't pick up the glass, take a swig of your cold drink and then lick your fingers. I strongly recommend you do not do that. Moving on, so we're going to look at dew point in a little bit more detail a little bit later on, perhaps in the next session. And that is crucial to understanding relative humidity, and certainly dew point is absolutely key to the successful design of a structure and for human health. And it's really something that is known is interstitial condensation. So we'll look at dew point, but we'll relate more to the fact of it's known in design terms as interstitial condensation, because that's what the design industry would recognize it at. Dew point is simply when the sun goes down, temperature drops very quickly, all the moisture falls to the ground, forms into liquid, and then when the sun rises, we get up in the morning, sometimes we see as light frost on the ground, or a light the ground froze, or we just see dew drops all over the grass, etc. And then the sun rises. As the temperature rises, that maximum potential starts to rise, so therefore the moisture evaporates and it's picked up by the warmer temperatures, and then the ground dries. But interstitial condensation, that's different. That's something very different, something that's critical to relative humidity. Something here, this is a fascinating thing. In 1783, this chap, Horace Benedict de Saussure, a Swiss physicist and geologist, made the first hair hygrometer using a human hair to measure humidity. Now, I'm sure we all know what a hygrometer is. You should do, because if you're reading the book along with the sessions that I'm providing you as well, you should already know that the equipment that measures relative humidity is the hygrometer. And as we see here, the first one was a human hair, which was all about the hair curling. So that the hair contains certain properties that reacts to moisture, and when it's dry, it'll stay straight, and when it becomes moist, it reacts and curls up. And the amount of curl, they actually made a hygrometer measuring instrument from it, and this is it, which is quite interesting. Well, I thought it was anyway. So when it comes to obviously relative humidity issues in buildings and structures themselves, we've learnt a lot from our mistakes in the past, our design mistakes. I certainly remember in the 70s, they built these new built houses. They absolutely crammed the walls full of insulation. They sealed just about everything bar the front door, not quite understanding the impact that was going to happen was actually through lack of ventilation, or appropriate ventilation, or condensation occurring within the walls, which is interstitial condensation, which I'll pick up in a later session. You can see from this image here the mould that's appearing on the walls. Now, it's not just at the bottom, which would indicate a rising damp, and it's not so much mould at the top of the room, usually in the corners of the walls and the ceilings, where it's really bad ventilation, and that's a classic sign where there's either moisture ingressing through the brickwork from perhaps faulty guttering, leaking through the mortar gaps in the brickwork, and it's coming in, creating mold issues there. This is all over. This is an example of really, really poor ventilation, and a big issue with relative humidity. So what do we do? What can be done? So, first of all, the main thing is we design this problem out in the first instance. That's what we do. We make sure as best as we can, 99.99%, this won't happen, because we do the calculations, we understand how the materials react as a result of their individual properties, and we just get it right. And this is a thing of the past. We don't see this anymore in new build houses. If we take a gym, for instance, a changing room, obviously that's an environment where there's lots of showers, or some showers, there's drying facilities, so on and so forth, and that's going to cause a lot of condensation. So what do we do to control that? So there's various ways. Obviously, not just design. First of all, we have to design for that particular environment in that scenario. So the expectation is there will be high humidity as a result. There'll be human beings in there, male or female, that are obviously they're exerting or radiating heat energy away from their bodies. You've got the convection currents around the bodies. They're exhaling moisture. They're naturally high body temperature through working out. They may have just had a hot shower. You've got the shower that's producing high humidity levels, pumping lots of vapor into the air. So the big problem is we're going to have a condensation issues everywhere. So we design with that in mind. So we'll be looking at higher levels of ventilation, and perhaps looking at more vent outlets that's extracting the humidity away, the steam, etc., etc. In an example like this, what we see here, obviously, perhaps the first thing we should look at is dehumidification. So a dehumidifier to go in there to initially extract as much moisture as possible from out of there. There are systems that do dehumidification, so we can design that process in, so it's not so much a ventilation, it's a dehumidification. We could put things like air conditioning units in there, but for a gym, I mean, yes, you can, yeah, but you'd have to take the approach that that could be very expensive, that there is maintenance issues involved with that, especially with air conditioning, with refrigerants and so on and so forth. Or we could maintain high temperatures within the changing room, and as a result of that, well, then you're not going to have a condensation issue. You're not going to have a condensation problem. But then you could say, well, saunas and steam rooms base on the same principle, where they keep the temperatures hot, they keep the temperatures high, but you still get condensation. You still get huge amounts of steam and so on and so forth. But that's a controlled environment. We've designed for that. So you just have to look for the main thing is we design the issue out. We don't let this problem occur in the first place. That's the main thing. Last of all, let's take a look at this. Now the thing with this is that it's just like a landfill, and I'm sorry to all dog owners, wet dogs are just like a landfill. Now, wet dogs aren't the sweetest smelling creatures, and sometimes they get a bit of a bad press, just like the landfill does with the smell of the refuse dump, so to speak. And is that in hotter climates, hotter days, etc. Certain people who live within the vicinity of a landfill generally don't get to smell on a regular basis, but when it does get really warm, really hot, the smell actually, what it does is the smell is actually aerosols, little droplets of odor, etc., just like perfume, which is little drops of odor, is carried within the potential of the temperature. So the hotter the day gets, the more molecules from the refuse dump, from the landfill, will go into the air, and it feels like these can carry for miles and miles, and it's just like a weather front. When we say like they're there's a hot air torrent coming up from the Gulf of Mexico, etc., etc. It can carry a long distance, so the warmer it is, the further it can go. But as you can see from the cartoon there, obviously the dogs love to get wet, but the owners are not so keen on getting anywhere near them when they're not so dry. So to the last, the dew point. So there we look at the typical blade of grass, and we got the dew on the grass there. As I said to you, this is a result of the sun going down. Typically, temperatures drop very quickly. You can see sometimes when you see in the weather reports about maximum relative humidity, maximum condensation. This is a common occurrence in winter when we get a nice crisp winter's day when it's bright and sunny all day long, and the temperatures rise to a balmy 11 degrees, and then come about 3 o'clock it drops dramatically. By about 5 o'clock it's 2 degrees, and then that's why we get ground frost in the morning, or ground freeze, is because the temperature dropped so quickly and the moisture just simply fell. Obviously on tropical nights, what we've had lately in this summer, where tropical night is classified as anything 20 degrees and above during the night, obviously it's very muggy, very humid, and there isn't any frost or dew point or condensation, because it's just frankly too warm, too much energy available for the water vapor to remain in place. Okay, so the next thing we're going to look at the a psychrometric chart, and this is where it all begins, and I'll explain why. Okay, so here is the psychrometric chart. First thoughts, I suppose, when you haven't seen one before, it looks quite complex, and there is an awful lot of information on that chart, I have to admit. But you won't believe how easy it is, honestly, trust me. What we're going to do, we're going to look at these different coloured entries on the left here. We've got dry bulb, wet bulb, relative humidity and dew point, and you'll notice that they're colour coded, and these arrows go in different directions, and that's to assist you as to where to identify the correct line against the correct meaning. So the psychrometric chart itself, it's got a lot of information, as I say, and a lot of this is very valuable to building services side of things, where you've got enthalpy at saturation, and that's kilojoules per kilogram of dry air. And then on the left, on the right here, we've got sensible heat factor. We've got moisture content, kilograms per kilogram dry air. That's an interesting one, because we can actually calculate the weight of the moisture within a classroom, for instance. So if we've got 350 cubic meters of air, well, dry air actually weighs, believe this or not, dry air weighs approximately 1.2 kilograms. Now that's just crazy, isn't it? I mean, how can air weigh that much? But it doesn't. That's because of pressure. But then obviously we can calculate the amount of moisture. We can take the reading from a whirling hygrometer or a sling hygrometer, or any kind of hygrometer, or a barometer that shows saturation pressure or relative humidity. We can take a reading off this, we can do the math, and then we can work out in terms of litres how much moisture is in the air. And just to give you an idea, that usually when we do the experiment in class, it's usually around about half a 2 litre bottle, so around about 3/4 to a litre of water, effectively, is what, and that's just crazy, because that's sitting in the air. But that figure drops in empty. I mean, there's lots of variables. If you're going to do it in an empty classroom and the air conditioning is on, it's very cool. You're not going to get that much moisture in the air, because there's not that much energy. You remember I spoke about energy earlier. The more energy, in terms of obviously energy equals heat. So the more energy in the air, the more potential it has to hold vapor. It's got a maximum potential 100% saturation per every degree. Okay, just remember the sponge. Okay, the classroom is a sponge. We go in there and throw half a litre of water into the sponge, and it's at 50% because it's a 1 litre sponge. Okay, so I think the next thing we need to do, we need to take a look at what these mean here. So we can see the first one we've got is dry bulb. Sorry about the flashing on the screen. I don't know why it does that, but it seems to be holding out. It's new technology to me. It's a graphic tablet, and it's ruling my life at the moment. Used to be the cat, now it's this. Right, okay, so let's take a look at the dry bulb. So we can see the dry bulb. Here we go. Dry bulb goes upwards in a straight line, and the dry bulb temperature line is at the bottom here. So all of this along here is the dry bulb. It's in degrees centigrade. There we go. So we can say, let's suppose that 15 degrees, here we go, there we go. So that would be dry equals 15 degrees centigrade. And we can see that the arrow corresponds here, corresponds to that arrow there. And then we go to the wet bulb, which goes at a bit of an angle, left to right at an angle. So if we actually look in a little bit deeper, we can see this is the wet bulb or saturation temperature, and it goes in this green line here, goes along there like that. Okay, so if we was to draw that, let's say 7 degrees. Okay, so 5, 6, 7. Oh, that's annoying. So we follow this line along there like that, and we just zoom in a bit, and there we go. We can see that at 7 degrees wet temperature, that goes in that direction, as you can see there, from left to right, and it crosses this line. And that's the most important thing, because wherever the wet and the dry cross, that's where all the information from the psychrometric chart is taken from, that crosshair point there. If we was to take the relative humidity, I really don't know why it does that, but oh well, we'll have to suffer it, I suppose. So the relative humidity goes up on that curve. So where the two cross, we can go through here like this, and we can follow this line up like that there. Okay, and a relative humidity, so if we had a dry temperature, let's say we had dry equals what did we say it was, 15 degrees, and the wet equals 7 degrees, then as the relative humidity comes through on this line here, we can see it crosses around about 20%. So that equals 20% relative humidity. Okay, now the other thing that we need to look at is, one of the most important things is dew point. I know it's going to change again. Yes, of course it does. So dew point is from right to left, and again we go through the epicenter here where those two meet. Okay, and all we need to do is draw our line, so we can see that it comes through just there, so we can draw it through. So let's start from about here all the way through to there. The reason I've taken it out to here, to over this part here, is because that's the reading. Okay, that's the reading. So we could now say that dew equals, so let's see, we've got 5, 4, 3 at 3 degrees. Now what that means is, at the moment we've got a dry temperature of 15 degrees and a wet bulb temperature of 7 degrees. What this is saying is that, oh, and by the way, let's remember that we're at 20 degrees relative humidity. Okay, just there. That's what this chart has given us here. We can see that here. We can see that's, whoops a daisy, come on. Right, we can see, let's change the pen colour, and then no doubt it's going to go again. Right, the wet is, ooh, it's got to stop doing that. The dry is given because of that, and then the dew is given on this reading over here. Okay, this really is annoying, this software. Now, what the 3 degrees means is that when this temperature it's going to go again, it's bound to go again. Go on, don't let me down. There we go. So this 3 degrees here is what we call the dew point. So it's the point at which condensation will happen. So when this temperature drops, when it drops from 15 degrees down to 3 degrees, that's when there will be 100% maximum condensation or maximum saturation. Now, it's important to remember that at 3 degrees, condensation if the temperature drops an absolute incredibly small degree underneath 3, so if it dropped to 2.999, that's when the condensation will happen. The dew point at 3 degrees is 100% maximum saturation. So it still won't condensate, but that is the temperature where it is at the dew point, the condensation point. So when it drops below that, that's when condensation forms. Okay. Right, so what we need to do then, we're going to look at the sling hygrometer and take a quick look at how those work, how we get the readings, and then we're going to do a quick example. In the next session, we'll be looking back again at the psychrometric chart, but what I will do is I will give you a link for where you can get a good psychrometric chart for you to practice with. We'll go through 1 or 2 examples together, then I'll give you a 3 or 4 to work on yourself for you to understand how this actually works. Okay, so let's take a look at the sling hygrometer. Okay, so here is an example of a sling or whirling hygrometer. It's fairly straightforward. We've got 2 thermometers. Both thermometers are absolutely identical. You can see one here, one there, simply a standard thermometer. Okay, absolutely identical to each other. Now, the difference between the 2 is the main gig, so to speak. If we look at the wet bulb, now the wet bulb is this one. That is the wet bulb. Okay, and we can see a wick here, like that. We can see it's like a cloth. I don't know what actual cloth is, but it's almost like bandage cloth. Nonetheless, it's a cloth that when we do the experiment, those of you attending college will be able to do this at request, no problem. I'll show you how to do it. You can do some research yourself and do some you can test in different environments and draw your conclusions that way. So this whole section here, this here is actually, all of that is put into the water. Right, a little glass of water, put it in, and we saturate the bulb. Okay, so we saturate this bulb here. This is completely saturated like that. And then the other bulb, obviously the dry bulb. Okay, let me just throw it in there. So this one is the dry bulb, just standard normal bulb. And what we do, we hold this part, and then we rotate this here. So we rotate, we hold it around about shoulder height, hold it out straight arm in front of you, and you rotate it for around about 30 seconds. And you spin it around about 2 to 3 revolutions per minute. So this here spins around about 2 to 3 seconds. Okay, and so what happens is, where all of this water is, the idea is that this evaporates. Okay, so as we spin, the drier the air, the more that this moisture, this water, will evaporate, and it will lower the temperature of the wet bulb. Okay, it'll lower, because the water, it evaporates quickly, which means that the dry bulb temperature, let's say the dry bulb was at 22 degrees, okay, and let's say that the wet bulb evaporated very quickly, and it gave a reading of, or let's say 12 degrees wet. Okay. In fact, we'll take a look at these measurements shortly. We'll see what that actually is on the psychrometric chart. But the drier the air, as in the air that has very little moisture in it, will mean that the wick here will evaporate very quickly, and it will give you a low reading, as in this here. It's just giving us a low reading of 12 degrees. However, when there's more moisture in the air, this wick here will remain saturated, or it will dissipate very little, which means that the wet bulb will be a much higher reading. Okay, much higher reading, and because the difference between the two is not very big, so therefore there's not enough dry air for it to evaporate. Okay, so let's take a look at what these values will look like in terms of relative humidity. Now, I think you can do the maths here, can't you? Remember the sponge. Okay, so the sponge equals, let's say, 1 litre, and then we put water into the sponge equal to 0.5 litre, and that equals 50%, doesn't it? So taking our analogy there, we can apply that here, and you can say, well, half of 22 is 11, so we would expect the wet bulb, or sorry, we would expect the relative humidity, let's just make sure we get that written there, relative humidity, that's what it would look like on my example of a sponge and putting water into the sponge. It would be at 50% relative humidity. So half of 22 is 11, so we've got this here. So I would imagine that the relative humidity might, let me have a guess, I think relative humidity, because we've got, so it's 11, so we've got 0.1 of that there, so I'm going for around 52%. That's what I'm going for, because we can, let's put a question mark there. Okay, that's what I think. That's what I think where we are. So let's do that. Let's try that, see what it looks like. Okay, so here we are back at the psychrometric chart, and we're just gonna erase all of this here, and then we're going to apply the readings that we've just looked at. So we said that the dry was 22 degrees, and then we can say that the wet bulb is, so the wet was equal to 12 degrees, and my guess equals 52% based on the sponge scenario. So the first thing we do then, we're going to do the dry bulb. Take a black pen for that. I'm going to take a ruler, and let's, whoa, that's just, this is crazy. Let's move that up there. Let's see if we can get this working properly. Okay, so that's not playing ball, is it? There we go. So going to dry 90 degrees. There we go. And we said that it was 22 degrees. So we can see 20, 21, 22 degrees. And I'm going to draw my line up there like so. Okay. move that away. Let's just put a little there. So we're going to say dry 22 degrees. Okay, now we're going to take a look at the wet bulb. Okay, so over here we have the wet bulb at 12 degrees, and we've got it at this angle here. So let's change the angle. And that's about right there. Let's line it up. Yeah, that's fine. So wet bulb at 12 degrees, which is here. Can you see that? Can you see that little dot that I've just made there? So we've got 10 there, 11, 12, 13, 14, 15, so on and so forth. Bring the ruler down to there. And then we're going to draw a line straight across. There we go. Let's move this out the way. In fact, we can get, well, just leave that there for a second. So there's our arrow. From there we can see that the wet bulb there, same angle as this here. So the wet was 12 degrees. 12 degrees. So now we've got these two crosshairs here. Everything, if you remember, everything comes through that. So the first thing we're going to do our relative humidity, which is this sweeping line here. Okay, and so through that crosshair there, I mean, you can zoom in on this and get really, really, there we go. Now, is this pen going to behave? No, it's not. So we can actually see, and I know what's going to happen. We're going to try and draw through and it's not going to let me. Yeah, thought so. So it crosses through just there like that, just under this line, just under, but we can take this through like so. You can see, actually I'm a mile out, aren't I? I said 50%, but I'm actually very, very wrong there. So, oh well, you don't know everything. Yeah, that is a strange one. However, it is what it is. So we've got a reading there, I would say, of around about 28%. Okay, 28%. So I'm wrong here. I'm wrong. That was my guess over here. There. And in fact, it was 28% relative humidity. Okay, based on these here. Now, what we need to do now is find the dew point, and the dew point being in green, let's just change that to green. So the dew point goes through this crosshair here, and you can see there that that is the right to left on a horizontal there, going through that line there. So we're going to take our ruler, let's bring it back to 0, and place it just there, and then we can draw our line across through here. And if we move the ruler away, we can zoom into that, and then we can get our reading. So let's just move this over there a second and then zoom in, so we can see we've got 0, then we've got 1, 2. It's around about 2.5. Okay, 2.5 degrees. So what does that mean then? Okay, so if we take a look at our temperatures, if we can find them again, there we go. Okay, so the dew point is equal to 2.5 degrees centigrade. So what that actually means is that we can see here that the dry bulb was 22 degrees and it was 12 degrees wet bulb, and my guess was completely miserable and way off target. It was actually 28%. However, what this actually is saying that at 2.5 degrees, if we was to suddenly drop this temperature down very, very quickly, very rapidly down to 2.5, that would make the wet bulb at 100%. So we would have maximum saturation or maximum condensation. What it would mean at 2.5 degrees, the dry air would be absolutely maximum condensation. In other words, it can't hold any more moisture or water vapor at all. And if we was to drop that temperature, drops to 2.4 degrees, then we're going to, that equals condensation. That means that the water vapor will change state from a gas to a liquid, and it will form moisture on the ground or on the window, or on the glass of beer, glass of pop that you had. We've reached the absolute, there is not enough energy in the air at that temperature to hold the amount of vapor, water vapor, that is currently there. Okay, hopefully that has made an awful lot of sense. I hope it does. If you look at that chart again now, it actually is quite easy to understand, and I don't mean to patronize anybody. We just remember the directions that these go in. The more you use a chart, the better it will be, the easier it will be. And as I say, in the next session, we're going to take a look at psychrometrics with a few more examples. That will link to Josh Hobday's maths. You'll be doing air changes per hour and various other mathematical techniques. What we'll be doing in the next session is, as I say, we'll be looking at that, and then we'll take a look at interstitial condensation. So in other words, this dew point here, it really is critical, really is very critical, and we'll take a look at what that actually means. Okay. Okay, so I just want to finish up this session with just a point that you need to look at. It's in your student book. Remember that we're talking about page 64 on this one, and really want you to look at this here, condensation. Condensation occurs when humid air with high water vapor content is cooled to below its dew point temperature. So I want you to read that, and I want you to understand the problems that buildings have and what affects buildings in general. Okay, so if you remember the exam type questions, they could come up and say, you know, a house has been diagnosed or under a dilapidation survey. There's issues with condensation in the cellar and in two of the upstairs bedrooms adjacent to the bathroom. Highlight to a client the reasons or the causes of why the condensation has happened. So you need to be able to recall that information and say, well, the activity of the building's occupants, what's going on there, what about the different types of appliances, gas appliances, etc., drying out construction materials, new builds, concrete plaster, and so on and so forth. Is it that there's an awful lot of things? It could be leaves in the guttering. There could be the stack pipe or the waste pipe that runs from top to bottom of the house on this two-story house, where it disappears into the ground and connects up with the sewer. That could be broken there, and it's creating issues, washing away the substrata, so to speak, affecting foundation. It could be a high water table. It could be flooding from next door. There is an awful lot of reasons why condensation may happen. It could be air bricks, not enough air bricks put into the brickwork at just above floor level. There could be the ground outside of the house has risen over the years in terms of vegetative matter has built up. It may have been originally a block paved drive around the house, block paved all the way around the house. Then someone may have tarmacked over that, which raises the floor level, the ground level, by another 30-40 mil. And then someone may have just come along and put gravel on top of that. So now the ground level has risen 3-4 inches, 5 inches even, which is now starting to affect the damp proof course. There may not be any damp proof course, of course. Oh, I'm a poet and I didn't know it. The point is look into condensation, look into why damp occurs in houses and stuff, and you'll find that condensation is a big factor, but it is curable, and you need to understand how these issues can be cured. But familiarise yourself certainly with what's being said here, and then investigate that a little bit further. Okay, and remember, answer the question and give the question back.